last years, which is an attempt to understand the black hole interior in the framework of the AdS correspondence. And the talks I'm going to give are based on earlier work that I did with Subrat Raju and some more recent work with this collaboration. Today, and the first two lectures I think will be a little bit introductory, and during the last lecture I'm going to talk about more recent stuff.
Was Lokhande an undergraduate at ISER Pune?
I'm not sure. It could be, yes. He was in India as an undergraduate, and then he went to Amsterdam for his PhD. Okay, so let me give some motivation. So the main motivation is that why we want to understand the black hole interior is related to the black hole information paradox, which I will briefly review, which is a fundamental conflict between general relativity and quantum mechanics. And as I will explain, it is connected to the question of what happens to an infalling observer when crossing the horizon. So these two questions seem to be slightly different, but during my first lecture, I will clarify the connection. And an important aspect of this paradox is that, in some sense, it is an IR paradox. So while we expect that effects of quantum gravity will be important in the UV and they may modify our understanding of space-time at small scales, this paradox suggests that there may be modifications even at large scales. In particular, it may be that our understanding of locality may have to be somewhat refined in theories with gravity. And also there is a concrete technical problem, apart from these general paradoxes, which is that the AdS correspondence gives us a very precise way to describe certain aspects of black holes. For example, we can compute their entropy, we can verify that the system is unitary. However, the question of how we describe the black hole interior from the point of the CFT is an open question. And it's an important question, for instance, if we want to understand how we can use the AdS correspondence to probe the black hole singularity. So today, I will review some of the stuff, and I will also formulate an analog of the information paradox in AdS. And tomorrow, we'll move on with some proposals for resolution and some recent developments. OK, so let me start by reminding you what is the black hole information paradox. So as you probably know, Hawking considered what happens when we quantize a scalar field in the presence of a black hole, which is formed by gravitational collapse. So we take some Klein-Gordon field propagating on this background. And then the point is that you can expand this field in modes. And there are two natural sets of modes you can select. One is the modes A, which correspond to particles coming in from scry minus. So these creation and annihilation operators correspond to incoming particles from the past. And another natural set of modes is given by selecting this as the Cauchy slice, this purple line, part of which goes along the horizon and part of which on scry plus. And then you get a new set of modes that we call BB dagger and CC dagger, which describe particles flying out to infinity and falling into the horizon respectively. And the same quantum field can be expanded in a different basis. And then the point of the Hawking computation is to find the relationship between these two expansions, which you can do, for instance, by taking the modes in the far future, propagating them towards the past, and see how you can express the late time modes on scry plus in terms of modes on scry minus. And as you probably know, the main point in this calculation is that creation and annihilation operators get mixed. So what is an annihilation operator in the future is a linear combination of creation and annihilation operators in the past. So in particular, if we start with a vacuum with no incoming particles, and then we compute the expectation value of the number operator of a mode B in the far future, we get something which is non-zero. So this means that we get some flux of particles in the far future. Now, another way of thinking about it, which will be useful for the discussion later, is to think about the propagation of modes through the collapsing geometry. And here I have plotted, we have identified a particular light ray, which is labeled by some particular advanced time V naught, where this light ray is the one that exactly falls on the horizon. And it's clear that light rays slightly earlier fall into manage to escape, while light rays which are slightly later fall into the singularity. So now if we consider a wave packet of the quantum field, which is concentrated in this small region, and we propagate it through this geometry, intuitively we see that this wave packet will sort of split in two parts, the purple and the blue one. one of which will fall into the singularity, and the other one will fly out to infinity, and these are the modes that we see as Hawking particles in the future.
We know this is an annihilation wave packet. It's a wave packet of nothing happening. Right? There's nothing really going.
Yeah, so this is just, it's not really an on-shell particle, it's just, this indicates how the modes of the field behave as you propagate them through this geometry. So this mode in the beginning is in the ground state. But in the far future, because in some sense you can think of the space-time as expanding, you get two particles which become on-shell. One of them flies out to infinity, the other one falls into the singularity. And the important point from this picture that we will use later is that this is the picture of pair production near the black hole horizon. The important point is that these two modes, when they become on-shell and they're created in the far future, they are created in an entangled state. So there's pair creation where the pairs are highly entangled.
Sorry, I didn't understand this wave packet describing what, I mean, if it's a pair production that is being described, you said it's a wave packet in vacuum, off vacuum.
I mean, you just take these modes that we had before, these modes, A.
So that is clear,
Yeah, and then you look at the solution of the wave equation, and you start the solution which has some data on this particular region, for example, and you see how you propagate.
Vacuum, right?
I'm sorry?
You want vacuum.
Yeah. So the only thing that we use from this relation is that so these are not on-shell particles, right? These are the behaviors of the solutions F and G and H. And the statement is that, so what we want to do is we want to find how to express the modes in the future, the wave functions in the future, in terms of the modes in the past. Once we do that, then we can also find the relationship between the operators which correspond to the creation of particles, the Bogoliubov coefficients. Yeah.
The Minkowski vacuum is not a vacuum seen by the Rindler observer, and then the Rindler observer's notion of particles becomes the correct one.
Right.
But Kyriakos wants
Yeah.
to point out that it's essentially a local phenomenon.
Yeah, so it's a phenomenon that happens near the horizon, and in fact, it's not so sensitive to what happened during the collapsing star. It's more, it is captured by the geometry at late times. It happens locally near the horizon, and
also happens locally in sky minus. This part of the wave packet.
that's right. So it's this particular region that sort of gets magnified by an enormous factor, and I mean every light ray so this little corner here represents an infinite amount of null space. Though it is, if you look at this geometry, this infinite region of space is mapped into this tiny region, the sky minus. So another way of saying that is that the modes that have low energy here, if you take a mode with a wavelength which is comparable to the size of the black hole and you trace it back, you find that it becomes transplanckian in the far past. So, and this is one of the subtleties in the calculation, whether the calculation can be trusted, given that these modes propagate through the star at energies which are transplanckian.
Except that they're not modes, they're just vacuum.
Yeah.
Most of the time.
Right. So another way, so also as Sandeep pointed out, it's a little bit like a Rindler and the Minkowski vacuum, and in particular, an infalling observer does not detect these particles when crossing the horizon. It's like the difference, which we will review tomorrow maybe, between a Rindler space and Minkowski space, Rindler vacuum and Minkowski vacuum. So, and in order for this to be true, in order for the infalling observer not to detect these as on-shell particles, it is important that they're entangled in a particular state. So the entanglement here is predicted by the calculation of Hawking, and moreover, I'm pointing out it is necessary in order for the infalling observer not to detect these particles as on-shell particles. So let me now summarize the result of this calculation. We find that if you look at a particular mode and you calculate the occupation level, B dagger B, you find that it is thermally populated up to some subtleties with the gray body factors that are not important at a temperature which is the Hawking temperature. And moreover, if you look at higher point functions of the modes B in the far future, you find that they factorize the 2-point functions. So this means that the radiation is Gaussian. It only is completely determined by the 2-point functions. Or in other words, these particles seem to be thermal and uncorrelated. And this implies that if you calculate the density matrix of the radiation at Scri plus, it is going to be a density matrix which is diagonal in the occupation level basis. So in Scri plus, we have a Fock space of particles. We can define a basis which is characterized by the occupation level of every mode. And this calculation is telling us that the final density matrix is going to be diagonal in that and thermal in that basis. Of course, then, if we have these particles flying down to infinity, the black hole loses mass and loses energy and slowly gets smaller. And after a long time, it evaporates. You can estimate the evaporation time. It's a very long time scale. And because of that, because of the fact that the evaporation time scale is very long, we can actually sort of apply this calculation of Hawking, which was done on a static background. So this calculation was done on a black hole of given mass. Now the black hole evaporates, so the mass goes down as a function of time, which means that the geometry is modified. However, because the time scale of the evaporation is much longer than the time scales which are relevant for computing the production of these particles, we can sort of treat the background as quasi-static and apply the calculation at any given moment in time, and then we can integrate and estimate the evaporation time. Okay, so it is believed that black holes evaporate, and then we're left with this outgoing Hawking radiation, which is in a thermal state. And this is where we have a paradox, because the calculation of Hawking predicts that we start with a state of a star which collapses, which could be a pure state. And under time evolution, we end up with a mixed state, which is inconsistent with unitary evolution in quantum mechanics, where the state is always pure. Or another way of saying that is that the final state, according to Hawking, seems to be to depend only on the mass of the black hole, not on any other detail. And as a result, you can have the same final state for many possible initial states of the same mass. And in other words, there's some loss of reversibility and information loss. Okay. Now, to make this paradox a little bit more precise, it is useful to consider the following concept. We consider the Hawking particles as they come out, and we consider, let's say, the first n Hawking particles, and we compute the reduced density matrix for those particles and calculate the von Neumann entropy of those modes. And since we already argued that these modes are independent, uncorrelated, then we expect that if you have one particle, if you take one mode, you will calculate some particular von Neumann entropy. Then if you take two modes, since they are uncorrelated, the density matrix will be the product of the two density matrices, and then the von Neumann entropy of two modes will be 2 times that of one mode, and so on and so forth. So according to the calculation of Hawking, you find that the entanglement entropy of the von Neumann entropy of the Hawking radiation seems to be linear in the number of modes that you consider, and in particular, it keeps increasing forever.
Just to understand that precisely, I want to understand what it means Hawking radiation, the entanglement entropy of the Hawking radiation. So is this okay if I draw a big shell and I look at the part of space-time outside that shell?
Yes.
And I count the entanglement entropy of that part?
That is the idea, right.
And that assumes that you can factorize the Hilbert space in some
Yes. This is a naive kind of estimate, which assumes we can define the Hilbert space of a region, or perhaps it can be made more precise by defining these modes of Scri+. Though I don't know if anybody has done it in detail, this calculation.
You should be able to do it. There are various subtleties just with making that notion of factorizability more precise for gravity, which are the analog of what happens in gauge theories. But at least based on whatever's been done in the gauge theory case, I think should probably be possible, up to additional infrared issues which might plague you.
But suppose, as you suggested, we work entirely on Scri+.
Yeah, even there, there would be the factorizability issue would be there.
The factorizability issue will be there, but there may be no further issues.
Yeah.
Because eventually everything comes out.
Yeah. Just this one thing which I haven't thought through, but some of you might,
Mm-hmm.
which is these gauge transformations at infinity, which they are tied to the factorizability issue in a sense.
Yeah.
Because in a sense, the factorizability issue has to do with gauge transformations at the boundary. So that's the only reason I put in that caveat.
No, I agree. But I'm saying if it's as good or as bad as gauge theory, that's fine. Right? But it might be seriously worse, right? Because complementarity, that kind of thing.
Right.
So I'd like to get rid of that more serious of the thing. And I think at Scri+, there's a chance you could just get rid of it. Right?
Yeah.
Everything comes to
Yeah.
That's the place to formulate it.
Yeah.
I'm not aware if anybody has attempted it seriously, but yeah.
Even at one loop, actually, if you just do free gravitons,
Yeah.
there's a bit of an issue.
Mm-hmm.
If you can do free gravitons, then at Scri+, you might be able to get away. You know,
Yeah.
just to do the free graviton case.
Yeah.
It's a great question.
Kind of issue that's the main point of his talk, right? That the Hilbert space of the black hole may be partly encoded in the radiation. So, you may think you're computing something of the radiation. Gravity may be highly non-local in the sense of Hilbert spaces. So this whole idea may not even be approximately correct, right? That if you, in the bulk, you break it up into 2 regions.
Yeah.
But at Scri+, as you
But at
said.
scribe plus, I think it should be.
Right.
And his graph, sorry,
Yeah, well.
his graph is best thought of at Scribe Plus, that you march along in Scribe Plus. Hawking tells you.
Yeah, though I don't.
So you do light cone quantization roughly, go all the way to infinity, and
Right.
this is half of space.
Roughly. That has to be precise, but I think
Yeah.
some parts.
So another related comment here is that if we want to make sense of this graph, I mean, here I have plotted what we expect for unitary evaporation. I mean, the final entropy has to go to 0 if the final state is pure. So this is what we would expect naively if the evaporation is unitary, while this is what we get from the Hawking calculation. And I mean, to address the previous concerns, it is important that this graph is about the exact fine-grained von Neumann entropy. Because in physics, we often introduce the concept of coarse-grained entropy. For example, that's the content of the second law of thermodynamics, that the entropy increases. So if instead of plotting the exact fine-grained entropy, you were plotting the coarse-grained von Neumann entropy, then even if evaporation was unitary, you would expect that the graph would just go up. And so to distinguish between the two, you have to compute the exact density matrix without making any approximation. And in the theory of gravity, that would require, that would perhaps not be possible because of the lack of factorization of the Hilbert space.
So in the CGHS black hole, people have computed Hawking radiation, right?
Yeah.
There do they try to get this notion precise of this curve?
Yeah, they did actually.
They do
There
Scribe plus?
Andy and so
You-
so on.
you-
Yeah. You can do it. It's so simple in 2D. You can even do it in other slices because you don't have any gravitons and so on. But you could try to do it as Scribe plus also. And there these issues are much less severe. And the ultraviolet cutoff is also a logarithmic dependence which you can take into account.
Okay. Right. So now, what are the possible resolutions of this paradox? So various things have been proposed, but given the input from the AdS correspondence, the most a reasonable expectation is that the evaporation is going to be unitary, and that somehow the information of the black hole is encoded in some small correlations between these particles. So the question is whether small corrections to the Hawking calculation can unitarize the radiation and resolve the paradox. Just a small comment, these small corrections are also what you get when you burn a piece of paper and you look at the radiation, where to first approximation it seems to be thermal, but if you look more carefully, there are small correlations. So just to make some comments, so of course we cannot calculate these corrections because that would be equivalent to being able to calculate the exactness matrix that you would need in order to that's a very important note, sorry. So we cannot yet calculate these corrections. So what we're trying to see is we will estimate what is the minimal size that we need for these corrections, and then we will ask whether we expect corrections of that order and whether those corrections are compatible with effective field theory. Also, when I'm talking about small corrections, it's important to keep in mind that we have to phrase the question carefully, meaning that we have to decide what observable or what quantity we're talking about, and whether that quantity has small corrections or not. For instance, if you look at the entanglement entropy of the Hawking radiation, obviously the corrections are significant. You want to take a mixed state and convert it into pure state, so the entanglement entropy will have to change by a lot. So later we'll make a little bit more precise which quantities we're going to assume have small corrections when the Hawking evaporation is unitarized. Okay, so now we'll try to argue that unitarity can in principle be restored by introducing exponentially small corrections to simple observables in effective field theory. So the Hawking calculation makes some particular predictions about correlation functions, let's say 2-point functions, 3-point functions, and so on and so forth of the outgoing particles. And we'll try to argue that based on general grounds, we expect that even if there are some effects in quantum gravity which unitarize the radiation, those corrections are going to be exponentially small in the entropy of the black hole. So they're going to be extremely tiny. And on the other hand, if we look at complicated observables, for example, correlation functions of a very large number of photons, where of Hawking particles, where the number of Hawking particles scales with the entropy of the black hole, then the corrections to these observables may be significant. And in other words, we should think of as the information of the state being encoded in these correlation functions of a very large number of photons. Now, to
all these correlations, do they have to be quantum gravity?
you mean the origin of these corrections? That's what we would think. I mean, as I said before, we cannot compute them. Yeah. Okay, so now to motivate these ideas, I want to remind you of a very basic result in statistical mechanics, which I will go into some more detail because I'm going to use it quite a lot also in the next two lectures. And it's a very basic theorem, very basic statement. I don't know what is the earliest reference. The earliest one I can find is the PhD thesis of Seth Lloyd. And the content of this theorem is to quantify what is the difference between a pure state and a mixed state in quantum statistical mechanics. And the intuitive idea is that if you have a large quantum mechanical system, then most pure states will look almost identical to each other when you probe them by most observables. So I will make these words a bit more precise in the next 5 minutes. And in particular, all these pure states look almost identical to the maximal mixed state. So let me try to quantify this.
You talked about computing exact density matrix, right?
I'm sorry?
You talked about computing exact density matrix, which would distinguish only that.
Yeah. So it will become clear. So here, the statement is supposed to be true not for all observables, but for most observables. So it will become clear that there are some quantities which can actually distinguish between the states. So let me now spend some time on this theorem to explain how it's proved, because it's very basic and we'll use it a lot later. So the idea is to consider a finite dimensional Hilbert space. So we consider a Hilbert space of dimensionality n, which also write as e to the s. And we will consider an arbitrary pure state in that Hilbert space. So we write down some pure state in this way. So this you can think of either abstractly as at the level of linear algebra, or you can think of them perhaps in physics as the energy eigenstates in a particular energy window. Now, what we want to consider is, so these pure states, this is the set of pure states. We want to introduce the notion of a typical pure state. How do we do that? Well, these are complex numbers that have to obey the condition sum of ci squared is equal to 1, because the state has to be normalized. And so you can think of the set of pure states as a sphere of very large dimensionality. So this is an equation for a sphere in a very large number of dimensions. And every point on this sphere represents a particular pure state. So this is the set of all possible pure states of the system. Now we want to define the notion of a typical pure state. In other words, we want to define a measure on this space, a measure on the space of pure states. And we will select the most natural measure in statistical mechanics, which is the microcanonical measure, which corresponds to assigning equal probability to every point on the sphere. So we introduce a microcanonical measure. B mu So we also have some overall proportionality constant that we select by imposing the condition that the integral of b nu is 1. So now we have introduced a notion of whether, if you consider a particular set of states, we can assign some probability to that set of states by simply computing the volume of that set using the round sphere of this metric.
And this is independent of basis, provided the bases are all orthogonal.
Exactly. So this is also called the Haar measure, because you can get it by starting with some reference state psi and then rotating it by all possible unitaries with a Haar measure. So in particular, it has the property that Shiraz mentioned, that it's a notion which does not depend on the basis. Okay, so this is the set of, it's a measure on for pure states. So these are pure states. It is also useful to introduce the microcanonical density matrix corresponding to this Hilbert space. So we also introduced the microcanonical density matrix, which is defined as the identity operator divided by n. So this will be the maximally mixed state, right? So now we want to consider how different are pure states on this set from the maximally mixed state.
And you get this by using the theorem that uij, ujk, u star jk integrated over all u is.
Yeah, that, I will get it in. I didn't get it yet. I will get it in the next.
This would be the total ignorance about the states, except that you have so many. This would be
Yes.
But you want that to be the same as that version.
I will show it in like.
Come in a minute.
It will, yeah.
Logically.
So now what we want to do is to consider so we consider some observable A acting on this Hilbert space, and I am not making any assumptions about this observable. It's just a linear operator acting on this Hilbert space. So now, the first statement is that if you consider the average over all pure states, so d mu, you consider the expectation value of this observable on a pure state, and you integrate over all possible pure states. Now, the first statement of this theorem is that this is equal to the macrocanonical average. This is sort of trivial. I mean, just 2 lines of algebra. It's based on some identity that Shiraz mentioned, or it's based on the fact that if you integrate these coefficients, if you look at the product of this form, it gives you delta ij divided by n, which follows from the fact that the measure is invariant under phase rotations, independent phase rotations. So in particular, this quantity has to be proportional to delta ij, and the permutations of the CIs also fix that the coefficient has to be independent of I, so you get that result. So this is also interesting. It's telling us that the maximal mixed state is in some sense the average over all possible pure states. What is interesting is the next part, which is to compute the variance of the different pure states. So this by itself is not telling us whether pure states are close to each other or not. In particular, this is true even for a small system, like a spin 1/2 particle. And so there's no content yet in this result. The next statement that we're going to discuss is the computation of the variance. So we integrate over all pure states, and we are taking the expectation value on a particular pure state minus the macrocanonical average, and we square this quantity, and we're integrating over all pure states. And to get now the result, you need so you expand the state psi in terms of the coefficient Ci, and you get things. You need to calculate things like Ci star, Cj, Ck star, Cl, let's say 4-point functions, which can be computed either using unitaries, some identities of unitaries, or by other methods. And you can, if you calculate this quantity, which is just simple algebra, you find that this variance is equal to 1 over e to the s plus 1 times trace rho m a squared minus trace rho m a squared. So this is the main point of this theorem, that the variance.
E to the s was n, right?
Yeah. So this is n. Yeah. Thanks. Okay. So this is telling us that if you look at this sphere of all possible pure states and you start varying, and you look at some observable A and you calculate the difference from the particular pure state to the maximal mixed state, this ensemble is the variance of that ensemble is exponentially small.
And you get that n plus 1 because you had 2 traces plus 1 trace.
Yes. So you have to expand this thing. You get the square of this guy, then. So you get various combinations, you have to group them together, and you get.
You could get a delta II, delta JJ, or a delta IJ, delta JI.
That's right. That's right. So you get this result, which is telling us that the variance among different pure states is exponentially small.
And largely, and at least this is more or less central limit theorem.
Yes, I think yes.
I mean,
Right.
the distribution for each will become Gaussian.
But
Right.
For a Hilbert space, not for.
For a Hilbert space.
Right. So now I want to make some comments about this. The first comment is that this is an exact mathematical identity which does not depend on the nature of A. It's true for any observable A. It could be arbitrarily complicated. It doesn't have to be, let's say, in physics, a 2-point function. It could be as complicated as you like. Right? This is an identity. Also, this identity does not depend on the dynamics. It does not depend on the Hamiltonian. Just some sort of very simple algebraic identity. Now, so in particular, this means that even if you take an observable which is very complicated, it's still going to be, its expectation value is still going to be typical. It will be almost the same on every pure state. So you cannot distinguish pure states by taking a very complicated observable. Now, when you look at this equation, you may think, what if what if this quantity is exponentially large for a complicated observable? Could that cancel the exponential separation. I think that is not like meaningful because one way of seeing that is that in quantum mechanics you can phrase any question you want to ask about the probability to observe this or the probability to observe that by using projectors. So even if you want to do a very complicated experiment which has some possible results, those results are captured by projecting your state on some eigenspaces. So at the end of the day, you want to calculate the expectation value of some projector, which may be complicated, but it's a projector, so its norm is 1. It's bounded from above by 1. So this quantity is bounded.
Can I just ask you about something which, if you were suppose your n-dimensional Hilbert space was because of n particles, each of spin half, something like that. If you were computing an observable which actually cared about all the n particles, even then this would be true?
Yes.
But it wouldn't be true if you tuned your
Yeah. That's the next point. That this is true only if you first fix A and then you take the average. If you correlate the observable you are using with a particular microstate you are planning to use to measure, then you can get around this theorem. For example, if you have the particular state psi 0 and you take the projector which is psi 0 is a projector, the expectation value of this projector on this state is 1, but on any other state it's going to be exponentially small. So in this case you have fine-tuned the observable in a correlated way with the state, and then you can sort of identify that you have this particular microstate. But if you don't do that, if you work with fixed operators, this is telling you that even if they're complicated, they will behave, they will have a nice typicality behavior, right? They will have the same correlators on most pure states.
On most pure states. But for any given pure state, there will always be some observable.
Yeah. Yeah.
For example, as you said, the projection operator.
Exactly.
Or something closely.
Right. Well, this is what we care is that this is bounded. So a projector, a projector has eigenvalues 1 and 0. So both these terms are bounded by 1, right? So then you get exponential separation.
Because trace row is 1.
Yeah, because trace row is 1. Now, this also does not, so it does not apply if you fine-tune, if you correlate the observable to the state. Also, this theorem does not apply for, let's say, non-linear quantities. For instance, if you look at the entanglement entropy and you try to think of it for a moment as an observable, even though it's not, just think of it for a moment as an observable. The entanglement, the von Neumann entropy is 0 for every pure state, but for the mixed state is maximal. So this theorem cannot be applied in situations where this A involves the density matrix of the state in some nonlinear way.
In other words, you're saying again that if it's a state-dependent operator,
this would not apply. This theorem would not apply.
So sorry, when we think about this measure as positive definite measure, is it that this whole integral is very small? Does that say that integrand is small?
This says that this is an integral over a positive quantity, right? So there cannot be any cancellations. It's always positive.
Unless the measure has something so.
No, the measure is very nice. The measure is think about a sphere of very large dimensionality, and take the uniform measure, just the round sphere, right? So the measure has no pathology. I mean, it's simple. You're integrating a positive quantity. If there may be some spike somewhere.
You can't say the integrand is small because we know that's not true.
Yeah, but on average, the integrand is small. Yeah.
I want to say that the final result of the integration is small, let's say.
Yeah.
So the result of any patch is small. But you can't say the integrand is small. Because we know that somewhere it goes high, as he pointed out.
Yeah.
I just wanted to understand this statement. I want to understand this statement because the integration is small.
Yeah, so it goes high over a very small region.
That integrates to that.
Otherwise, all other traces it is very small.
Yes.
The denominator is the volume sphere, right?
This one? Yeah, probably is not.
No, I mean whatever the measure gives you, integral give you with 1.
Yeah, we have normalized the measure to be 1, right? The integral to be 1. So let me also make a few more comments. the fact that most states have to look equal to each other and equal to the maximal mixed state does not mean that you can not find an atypical basis of states. For example, take a spin chain. A spin chain up and down, right? If you take a typical state, a random superposition, the expectation value of every single spin will be 0 up to exponentially small terms. But you can certainly take a basis of eigenstates of the spin where it's either plus 1/2 or minus 1/2. So you can always select some basis, complete basis of the Hilbert space where every single element of the basis sort of violates this theorem. Not violates, I mean, yeah. Yeah, suppose we take a spin chain. So we have like some system with spins up and down with n spins. And we write down the most general superposition. So it will be some superposition of states with particular kind of distribution of those spins, right? If you take a random superposition and you compute the expectation value of the first spin, it's going to be extremely close to 0, right? Because there are all these cancellations. So the microcanonical average for the spin is 0. However, if you take each of those states, which is a basis of states, it's either plus 1/2 or minus 1/2. So every single element of the basis sort of is giving you a large deviation from the microcanonical average. So it is possible to find a basis of atypical states.
I see. Okay.
You're saying not just is it possible to find, we knew there was possible to find one, you're saying it's possible
Yeah, to find a basis actually, yes. And this may also be a bit relevant for like these fuzzball ideas where people try to find out some class of states, and then the question is whether those represent a typical state or not. Perhaps there's some atypical basis, but we will come to this tomorrow.
It's like this Kukuyo-Manleke.
Yeah, that's exactly. These are some states in the SYK model that we will discuss on the last day probably, which are selected by hand in a sense to be atypical, and they form actually over complete basis of the Hilbert space. One more comment. This does not assume the eigenstate thermalization hypothesis for those of you who have worked with it. So this is more basic. It doesn't require the ETH. And finally, one more comment. The fact that the variance over different pure states is small does not mean that the quantum variance of an operator in a particular state is going to be small. These are two different quantities that should not be confused. So, for example, in the case of the Hawking radiation, if we calculate B dagger B, the number operator on some state psi, we find the thermal result. But if you take the square, you find something which is not just the square of the number operator. So there's some quantum variance. What this theorem is telling you is that the quantum variance is going to be almost the same on most pure states. And finally, as we already said, this does not mean you cannot distinguish pure states. If you work very hard to identify particular observables, fine-tune the state, then you will be able to sort of identify the microstate. So usually, and in the rest of these lectures, I will simplify this statement by a less precise equation, but it's sort of more intuitive maybe, which is that for most states, we have this equation, that these two quantities are exponentially close. Yeah, but keep in mind that this equation is true only if psi is a typical state. It may be violated if you select the state psi in a particular way. And finally, remember this was for the comparison with a microcanonical ensemble. Now, extrapolating a little bit forward, we will also want to compare pure states to the thermal ensemble. And then, so this is not part of the theorem. It's now a new statement. But I'm just mentioning it for completeness. When we will also try to compare the canonical expectation value, but then the corrections are going to be suppressed by the entropy. They are not going to be exponentially small. And as we will discuss later,
but this canonical row corresponds to the same energy or something.
No, yeah. So here we have to, so now, I mean, there's a lot of things missing here. So we have to think of this as an energy window of some Hamiltonian. And now we're writing down the Boltzmann density matrix for this Hamiltonian. But as far as I know, there is no proof of the statement. So it is a plausible assumption in statistical mechanics that you can interchange the ensembles. But I don't think there's a proof. And in fact, this will become important later.
Okay, but when you learn the first course in quantum mechanics,
yeah, you have to make some assumption about,
the density of states is growing fast.
Exactly.
Then that grows fast.
Yes,
E to the minus.
that's right.
Yeah, et cetera, et cetera.
Right, but there's one more thing, which is the behavior of the observable as a function of the energy. So if you want to compute the expectation value of A, you need the Boltzmann separation, you need the density of states times the the diagonal elements of this guy. So if those fluctuate very rapidly, very dramatically, these approximations may not hold. So
Okay, so there's some assumption there.
yeah,
That they fluctuate.
right. Okay. All right. Are there any more questions about this?
Yes, so this typicality of state, even this first equation, that depends on A, right?
Sorry, this equation here?
Yeah.
This one?
Yeah, I mean the one that you talked about. Yeah.
This one? No, it does not depend on A.
So can you say again what is typical of A?
Well, if you want to, if you compute an expectation value on some state psi of an observable A, you will get some result, right? Some number. If you change the state psi, you will get a different number. If you change it again, you will get yet another number, right? Now, we don't care about every single result. We care about the average of all those results. And that's why we introduce a measure on the space of pure states, and we integrate over all possible pure states. And typical states, by definition, are a set of states is typical if it occupies, let's say, most of the volume of that manifold.
But that depends on the operator, right?
No, no, no.
If the operator is a projector, then
Yeah, if it's a projector,
state that was typical for different observable is not. I mean, if it's a projector on that typical state.
no, I don't. It's not very clear to. If you take just one state, you cannot really call it typical. I mean, the typicality would be for a set of states.
But okay. But the projector would just be on that set of states.
Well, the projector will give you an exponentially small result here, right? So which is telling you that for most states, if you compute the expectation value of the projector, you will get something which is very, very small. And there may be some.
No, I'm saying that if you're giving me a set of states, calling them typical states,
Yes.
I will give you an operator for which the expectation value computed on those states differs quite a lot from expectation value computed anywhere else.
That's possible, but
For that operator, those will not be typical anymore.
well, but first of all, you have to tell me the set that you gave me in the beginning. What was the volume of that set? Was it small or large? If it's small, then I would.
So that's small, right?
Then I would tell you you're not allowed to call them typical states by definition. I mean, if you want, you can forget about the term typical. You just look at this identity, which has some particular content.
If you assume a size of the operator, by size I mean that the states on which this A has a non-trivial value for this integrand. Once you assume that there is this part of the sphere which sort of has
Yes.
non-zero value, then that gives you a bound using this theorem on this integrand for those states which contribute significantly.
Well, it's a combination of the volume factor and the integrand. Yes.
So because I am saying that only this part of the sphere contributes significantly
Mm-hmm.
for a given operator A, this part of the sphere contributes significantly.
Mm-hmm.
So this theorem bounds
Yes. If
contribution from this part by some number.
yeah.
Now, would it be that if I'm saying that, say you have two operators A and B,
Mm-hmm.
and this is like a 2-point function, which is say significant for this.
So you do it like this, A times B.
Let's do.
Yeah, but you can just apply the theorem directly on A.
But
W.
you can have A as a parameter T, A at T and B at 0. Like it can have some non-trivial time dependence. So what I am saying is that
There's no time dependence here, right?
I know,
Yeah, yeah.
but what I am saying is that in general when operators evolve in time, they are
Oh, yeah, yeah.
on the Hilbert space increases.
Yeah, yeah. Whoa,
Suppose you have a
whoa, whoa.
local operator at some instant of time. As you time evolve, because of the Hamiltonian, it sort of increases support.
It becomes more complicated. I agree with that, but it's certainly true that if you take a state psi and you do time evolution, it may sort of
If you
become.
have a span on, even if it was a local state, the local
No, no.
operator,
Well, are you talking about the state? The states. I mean, the volume is preserved, right, under unitary evolution. So if you start with a set of states and you evolve them, they will sort of the volume will be the same. Now, it can happen that a state which used to be close to the average, under time evolution, will go through some particular time interval where it goes out of far from the average.
Yes, what I was just saying, if I take AT times B at 0,
Mm-hmm.
and let's say AT times B at 0, some
Mhm.
amount of time at 4 level,
Yes.
and then if I a priori say that this is non-zero only in this part of the sphere, that gives you a bound.
Yes, if you can find a way of like selecting the region of the sphere where it's, I don't know, maximal or whatever you want to say, yeah, it'll give you a bound. Okay, so okay, let's think for a second. So now I have 10 more minutes. Is that correct? Yes. Okay, great. So
I mean,
yeah.
You may get exhausted at some
Okay, no, it's fine. So
maybe you can even go past 1:30. I don't know.
okay, great.
Obviously, this is the online time.
But this counts as one lecture. Or
Yes.
okay. Fine. Great.
Now when you get to 2,
Okay.
You can give more than 3 if you feel like
All right.
we are
Okay,
happy
great.
to hear you.
Okay. So then another kind of statistical thing that we will need is this analysis of page, which I will briefly mention without going into many details. It's the idea to select a big system and divide it in 2 parts, A and B, and consider the big system to be in some pure state, psi, and then calculate the entanglement entropy of the reduced system, let's say A. And you can do it, I mean, the best thing is to just do it for a spin chain. It's a very simple calculation to take one spin out of a spin chain, and you try to calculate the reduced density matrix. You have to do some integrals very similar to the ones we wrote down here, and you will find that if the system A is small, then the reduced density matrix is exponentially close to the maximally mixed one. And in particular, its entanglement entropy is proportional to the logarithm of the dimensionality of that density matrix. So in particular, in the beginning, when we increase the size of A, the entanglement entropy increases linearly with a log of A, of the size of A. But when you do this calculation, there are some off-diagonal matrix elements that, well, in the beginning they're exponentially small, but as you make the subsystem larger and larger, the size of that Hilbert space becomes exponentially large. So there's some interplay between those small corrections and the size of the Hilbert space. And once A is a significant fraction of B, those corrections can no longer be ignored. And in particular, since if the full thing is in a pure state, we know the entanglement entropy is symmetric between A and B. So we expect that when A is almost all of the system, then the entanglement entropy will go down. So sorry, I've made a mistake here. This should not be 1. This is when this ratio is yeah.
Wait, even if it's like a finite energy density state, shouldn't the entanglement entropy grow like volume for a while at least?
Yeah, this is the size of the Hilbert space, not the size of the system. Sorry. Yeah, I'm sorry. This is the dimensionality of the Hilbert space. Yeah.
Just very similar, of course, you said very nicely for a spin chain, but just, very similar to the manipulations you did with the R measure. If you just take a tensor product Hilbert space, and you take a typical pure state, then because of the coefficient, you can repeat
Right,
this,
right.
and
You get
the same.
right.
Just from the indexology you said.
Right.
And that A, I mean, it's really precise that B over 2, right? At least for a typical state. Because entanglement entropy is determined by the size of the smaller system.
Yes.
Yes.
So it's really a B over 2 for a typical state.
Are you asking the fact that there's a kink, or
Yes,
the fact that it's
the
exactly?
maximum happens at B over 2.
That's exactly as you said. It has to be there. I don't know if it has to be very sharp. Probably it's very sharp in some large n limit, but
I think it's probably not very sharp.
yeah. I don't know if to what extent we can control that analytically, but probably I don't know. Yeah, I don't know.
But the width of that is probably.
So this is not a plateau, right? It should be some. I'm sorry, it's misleading the diagram.
I
Yeah.
think it's a reasonably smooth curve.
Okay.
I remember working around once,
Okay.
using your unitaries,
I see.
but
Yeah, I'm sorry, I don't remember. Yeah.
Why does this apply only to the typical pure state, not any pure state?
Well, for example, you can take a pure state without any entanglement. Just take a spin chain where all the spins are up, right? Just up. Then the entanglement entropy is 0, no matter how big the system is. So
you have to say which region and so on for a particular pure state.
So to prove this theorem, we have to do, as Sandeep said, some integral over some unitaries, and those are motivated by the fact that we're looking at a typical state. Okay. Now, the implications for this, the Hawking evaporation is the following. We expect that if evaporation is unitary, then the entanglement,
And it's symmetric? This curve is symmetric?
Yes, it's symmetric, because if you have a pure state and a bipartite system, the entanglement will be symmetric. Also, another statement is that if you take a typical state, and if you take a small, let's say,
Sorry. But this is, whenever people say page curve, this is the full content of that.
Yes,
It's
that's
very
right.
simple.
That's right.
Nothing deep.
Yes. Now, one more statement is that if you take this typical state, you have A and B, and you take some, like say, a third qubit, and you pull it out, and you look at the entanglement between this qubit and A and the qubit and B, you find that for typical states, a third part, a small part of the system is mostly entangled with a larger of the two Hilbert spaces. That sort of makes sense.
Please say that again.
I mean, if you have, for example, a spin chain, and so we have a spin chain, and we take the first spin. I'm sorry, we have a spin chain, many spins, and we take the first spin, and then we divide the remaining spin chain into two parts. Let's say A and B, and we ask the question: is this guy mostly entangled with this guy or with that guy? And the answer is that on a typical state, it's mostly entangled with a larger part of the Hilbert space, which sort of makes intuitive sense.
Because it's typical. In an actual physical state, the guy may be more entangled.
Yeah. Of course. But if we imagine that somehow the thing has fully thermalized, it's totally like randomized, then this guy, will be mostly entangled with a larger part of the Hilbert space. Now, the implications for the Hawking evaporation is the following. We have two systems. We have the black hole, and we have the radiation that has been emitted in the past, right? So we have the black hole, and we have the radiation that is going out. And as time goes forward, this black hole gets smaller, and this gets bigger. So the Hilbert space of this black hole, we can sort of estimate dimensionality by the Bekenstein-Hawking formula. And this one, we sort of argued it.
Sorry. Is there an estimate for the ratio of the entanglements? Is that basically the ratio of the Hilbert space sizes?
So I have not reviewed this recently, so I cannot give you a reliable answer right now. But
like that, right?
I suppose it should be possible to work it out for a typical state. Yeah. So now the idea is that if we have this Hilbert space grows in size, this Hilbert space decreases in size. If we assume that the total state is somehow thermalized, is randomized, is close to typical, then we expect that any new particle that comes out, any Hawking particle that gets out, we assume that at the early stages of the evaporation, it has to be mostly entangled with a black hole because a black hole has a larger Hilbert space. So before phase time, we expect that the new Hawking particles have to be entangled with the black hole, while after phase time, they have to be entangled more with the outgoing radiation.
And at least for coal, this is true. Right?
Yeah, for any toy model, you can write down like coal, burning piece of paper. This you can explicitly check. I mean, Mathur has written a few toy models where he has tried to check this explicitly, and it is true.
That makes sense.
Yeah. Okay.
And this assumes that the black hole Hilbert space and the radiation Hilbert space are distinct Hilbert spaces.
Yes, that's right. Okay. Yeah.
This is very elementary, but how do we know that the Hawking density matrix is a thermal one? I mean, given that there is this equation here, where you compute an observable in the pure state and also in the canonical density matrix, you get almost the same modulo these corrections here.
Are you asking me, should we model it by this one or that one? Is that your question?
Hawking calculates actually the density matrix. Doesn't compute observables. It just gives you the.
But this is not to be. This is not proved that with some operators or.
No, it's just you take the state and evolve it, and you find the density. So the unitary evolution of the state gives you a density. So the way you calculate is you compute the density matrix, and from there you can calculate whatever you want.
So these kinds of arguments don't enter into it. So that
It's just-
approximate density matrix and so on.
No, if you just calculate, I mean, within his approximations, he just evolves this pure state into a density matrix, and it's there in front.
What is the order of this time?
Let's say, well, it's not 1/2 of the evaporation time. It's of the order of. Well, this is not. I'm sorry. This should have been the number of the entropy, not the time. So the middle is not the half. it's not the half point in terms of time, but in terms of how much entropy it has lost.
Half of the entropy.
Half of the entropy, that's right. Regarding the previous comment, also this theorem cannot be applied to the full density matrix, right? I mean, as Siraj was saying, like, Hawking calculates the density matrix in principle, and you can say, what if we try to apply a theorem like this for the density matrix? That is not allowed, right? Because it's a state-dependent object.
Can I say
Yeah.
one thing towards what Jeet was saying? Because this, I feel, is kind of a crucial point. Hawking's calculation actually is consistent with a, if I may say, infinite Bekenstein-Hawking entropy in the following sense.
Mm-hmm.
If you include the entanglement as part of the definition of the entropy, then you really get the area of divergence. So the full entropy in that sense is actually infinite. And that's where the thermality is coming, because shorter and shorter wavelengths, which are entangled across the horizon, are contributing. So in a sense, in that approximation, you are treating the total black hole entropy as infinite. Although of course we say it is area over 4
Right.
Newton,
Right,
it's
right.
actually area over epsilon squared, for an arbitrary small epsilon. And that's why you get a thermal answer in the end.
Right.
If there was a way to, we don't
Yeah.
understand yet how the ultraviolet cutoff is generated to give for the full entanglement, for the full entropy,
Yeah,
area
yeah.
over 4G Newton.
Right, right.
If there was a way to do that, then automatically it should give
Mm-hmm.
the page curve turning.
Right.
Somehow, right? Okay, just
Is this the same statement that the correlations between these two photons extend to all energies? And if that was cut off at very high energies, that would show up in the...
Yeah, that would show up, because you see, as Kiriakos was emphasizing, it's very short wave. As you wait later and later, actually,
Yeah.
it's shorter and shorter wavelengths that make that
Right,
make up.
right.
And if you did it in some crazy, like a brick wall cutoff, it would totally change. The gravity is much more subtle, of
So
course.
suppose you put a lattice on the black hole back and did the Hawking's calculation. That would have your cutoff.
Yeah, that would be drastically different. Drastically different. The moment you go shorter than that, because that wavelength is actually red shifted.
But that would destroy the smoothness of the horizon, I suppose, not the...
Then you would, then you have to make that consistent with why somebody falling in. This takes us to the whole issue of how do you then reconcile the smoothness of the horizon to all I was emphasizing was somehow the smoothness of the horizon approximate is consistent with area over 4G Newton.
So that was one of the main criticisms of Hawking's original derivation, right? This trans-Planckian problem, and where you are considering modes which are beyond your effective field theory cutoff.
It's related to that.
Yeah.
But let me understand, is there a problem in technically doing this calculation with the lattice? Is there a problem of putting the lattice in a generally covariant way? Is that the problem? I mean,
if you cut off the momenta at some Planck scale,
let's put a real lattice, like the QCD lattice, on this background. Forget about gravity. Gravity is not important.
But the space-time keeps stretching, right, near the horizon.
Keeps
So how will you deal with the cutoff?
What is your lattice?
But if you did it in terms of a local inertial frame, somehow defined, you have to choose a preferred frame. Then you would do it. Then it would be very drastic in terms of the implication.
And you want to maintain general covariance.
So
That will be very tough.
it's very tough. You'll have to choose a frame, and then you'll have to adjust the frame for some local fall. You could try to do it, but it will
Suppose I
be
do
drastic.
dimensional regularization. I put a cutoff. There should be some way of doing a field theory calculation with some cutoff, explicitly. And I take the mu seriously.
I think if you preserve
but the
Lorentz
cutoff
invariance,
is
you'll
to be
always get the divergence. Preserve Lorentz invariance, you'll always get the divergence.
What is the scale of this cutoff, given that you want the entropy to be just the area?
Roughly, but you don't know what it is exactly. But
So sorry, how
it's,
to see that?
just because the entanglement has an area law divergence, area over the cutoff square, and the Bekenstein-Hawking is area over L plan.
Okay.
But gravity does it much more deeply and subtly somehow.
Are you saying that the key point about gravity is that it's impossible to make a Lorentz invariant cutoff? I mean, the fact that you get something so interesting related to the fact that you cannot make a Lorentz invariant.
But gravity does it somehow.
So the key point about gravity is the only way of
Yeah.
string theory.
Yeah.
Okay.
Yeah.
That's interesting.
Okay. Let's see now.
It's not the issue of regularization also, right? The dimensional regularization that
they somehow remove the low and the short distance fluctuations, Sandeep saying things would change very much. Because short distances go to what? Later times.
So this has become long distance at late times. Yeah.
And the longer you wait,
Yeah.
like by the time you wait, go to the page time, it's
Yeah.
a really huge redshift.
Yeah.
I was just wondering whether we could, in Lorentz covariant, generally covariant way, more than even Lorentz covariant, do what Sandeep's saying in a calculation. But it's probably tough. It's probably.
Let me just say one more thing. Please do go.
Yeah.
You know, there's a very nice version of this issue which Atish had identified a long time ago, which is let's try to compute the entanglement entropy using the replica trick. That means that you work on a cone. You know, the way you do the replica trick is you introduce a cone and then you take the derivative.
Yeah.
And then the conical deficit is not always a disaster in string theory. But it became, the UV issue became, as usually happens in string theory, an IR issue with tachyons. And, the way string theory does it is just incredibly deep. I mean, somehow compared to a dumb.
Whitton had a follow-up paper on this a few months ago.
He had a follow-up paper.
The paper on Satish business.
Yeah.
Oh, open strings on the Winter Horizon?
Yeah.
We should read it. So
Yeah.
That's true.
IAS is always following up on DI.
Okay, so we have made these remarks so far, and we argue that this kind of consideration suggests that even if there's some mechanism that unitarizes the radiation, the correction will be exponentially small. And so far, however, everything we have said had to do with what happens at Scri Plus, and we did not pay a lot of attention to what happens near the horizon. And now we'll address the question whether this idea of having some corrections which come from quantum gravity, how it can be reconciled with the smoothness of the horizon. And as we will see, this is a more difficult aspect of the problem. So let's start with some more kind of older ideas, why the black hole interior plays a role in the information paradox. It's a very simple argument. Well, it seems to be a simple argument. You consider the evaporating black hole, and then you can find a space-like slice that's called a nice slice, which you can check that it has a low curvature, both extrinsic and extrinsic everywhere, and also the velocities of the particles on the slice are low. And then this slice can be stretched like that near the horizon sufficiently so that it captures at least more than half of the Hawking radiation, as well as a particle that you throw into the black hole earlier. And then it seems that if the information of this particle is encoded somewhere on this slice, then we have sort of cloning of information, which seems to violate the no cloning theorem of quantum mechanics. So from this, we see the importance of the interior, because if you ask the same question for a star, if you throw something into a star, you would not be able to do this, right? You would not be able to find a slice by exploiting the gravitational field and deforming the slice in space and time. You would not be able to find a slice which captures the particle both in the interior of the star and also in the outgoing radiation.
I just say the last thing. So therefore, you should not. There might be something wrong in the slice, or the interior is not independent of the exterior.
Yes, right.
Perhaps say.
Right.
But could it be that there's, just to ask you, could it be that there's something wrong? I understand the slices seem very nice, but could it be that somehow the rules are that such slices with large stretching or boost?
Yeah, I guess various people have discussed that maybe there's a very large relative boost between these two regions, and if you actually compute the space-like length, it's enormous. It's like orders of magnitude bigger than the horizon of a black hole. And also, if you think about it, the time scale, the proper time from this point to that point is like a millisecond, right? If you fall into a solar-sized black hole. But this proper time is 10 to the 60 years. So the stress of these slices in time is huge. And they may be pathological, but as far as I know, nobody has found a particular technical problem to argue that effective field theory on these slices will break down. Okay, so so one way out of this paradox, which was suggested by these people in the old days, was that to say that perhaps there is quantum cloning, but is there any observer who can actually detect it? And the idea then is that there is a qubit here, and the infalling observer can see it. There's another copy of the qubit outside. There's another observer who can see that, but there is no single observer who can detect both copies of the qubit, and as a result, perhaps we shouldn't worry about this cloning. Or another way of phrasing it, which I don't know if it's exactly equivalent, but is that perhaps the idea that we can factorize the Hilbert space into the region localized here and the region localized there is not true in gravity. So if this is not true, then it means that whatever qubit you have here may actually have secretly some overlap with the Hilbert space which is already there, and hence it's the same qubit. There's no cloning. The problem with this idea is that it's not so easy how to, I mean, first of all, you have to find the mathematical realization of this idea somehow, because this is just words at this point. And second, it's not obvious if you do this, if you assume that the Hilbert space does not factorize, it's not clear whether effective field theory, locality in effective field theory will be a good approximation. For example, if you test it yourself by taking some Hilbert space and trying to realize some observable as a scrambled operator acting on that Hilbert space. So you take some qubit, some spin operator, and then you conjugate by some random unitary acting on this Hilbert space, and then you estimate the typical size of the commutators. You find it's order 1. So the idea of complementarity is that the interior is somehow scrambled and encoded in the Hilbert space of the exterior. But for this idea to be compatible with the fact that in effective field theory operators approximately commute is quite non-trivial. It's not something that comes out naturally if you just write down some random scrambling unitary. Now, for this to be consistent, this idea, of course, we have to make sure that there is no way that this guy cannot capture the particle, detect it, and then jump into the black hole to see the second copy. And there's a basic consistency check you can do, which is to imagine that you throw a qubit in the black hole, then it has some rocket, and then it starts flying parallel to the horizon. And then you wait a little bit outside, you capture the Hawking radiation, sufficient amount of radiation to extract the qubit, then you jump in, you try to meet the qubit. If you were able to do this experiment in effective field theory, that would rule out this idea. But then you can verify that the amount of time you need to wait in order to extract the information is case like beta log S. This is the result of Hayden and Preskill, which I will discuss maybe a little bit later. So for now, just accept that you can extract a qubit, the information of the qubit, by waiting this amount of time and collecting the Hawking radiation. But then, in order to be able to meet this particle, this guy has to move with a very high boost. And if you plug in the numbers, you find that in order for this to be able to not fall into the singularity for this amount of time, then the energy of this particle B would have to be Transplanckian. So it's not possible to formulate this problem, this procedure in effective field theory. And so this idea of complementarity passes a basic consistency check.
So energy in what frame?
In the frame of the local frame of this guy. Yeah. So he's freely falling, right? He's at rest in his own frame, and he has to send a light ray, like backwards.
So let's say the rocket falls in. In his frame, he would have to
yeah.
send a transplant.
Right. Oh, sorry. Yeah.
And what's going on is that something just how does that work? That
I mean, normally
very near the event horizon gets redshifted.
Yes. That's one way. If it travels parallel to the event horizon, it gets redshifted. So if you want to survive for long enough, you must have very high energy. Now, okay, so this was the proposal, but then more recently, a few other paradoxes have been pointed out, and one of them is the strong subactivity paradox, which was first formulated by Bantour and then discussed more with Amps. And we already have the ingredients. We already said that these two guys have to be entangled if we want the infolder not to see anything. And we already said that after phase time, this particle B is mostly entangled with a larger part of the system, which is the early radiation. So it seems like this B has to be entangled with two different quantum systems, and this violates monogamy entanglement. And you can quantify it a little bit more carefully using strong subactivity, though there are many subtleties here, because as we discussed earlier, you have to be able to define what you mean by SAB in a theory of gravity, so you have to be able to sort of factorize the Hilbert space. But anyway, at least naively, it seems there is a paradox here. And Samir has also checked that if you modify the quantum state a little bit here, you cannot get out of this inequality. You still have a paradox. Yeah.
Can I ask a very simplistic question? So let's say you somehow think of this black hole as a Fermi sea.
A Fermi sea.
With a bunch of electrons entangled in ellipsoids and so on. And if an electron comes out,
Yes.
okay, and then you see it, and corresponding hole is created.
Yes.
So what is wrong in seeing both the electron and the hole?
Well, it's a question about the entanglement. So what is it?
Could be entangled.
Right, but if we want to restore unitarity, then this electron that escaped from the Fermi sea, it also has to be entangled with whatever electrons had been emitted long time before. I mean, if this is the first electron that comes out of the Fermi sea, it's like being here on this part of the diagram. And then there's no paradox. What you said can be perfectly true, right? But if half of the Fermi sea has already evaporated, it means that the new electrons that are being emitted, if the evaporation is unitary, they have to be entangled with the earlier electrons. So they cannot be entangled with a hole at the same time. So
And also when one talks about electron holes, there's a question of what vacuum you're quantizing about. So when one talks about holes at early times in the black hole, one is talking about the vacuum where the hole about the Fermi level. But when you late times when you talk about the Hilbert space in the black hole, you're talking about the vacuum of the true vacuum, right, where there is no all the electrons are common. So
well, maybe I should say you can actually formulate it as an experiment. Maybe I can phrase the experiment and you can tell me if that addresses your question, rather than discussing this vacuum. The question then is, so at this point you could say, fine, there's a violation of this inequality, but we don't care because there's no observer who can measure both entanglements, as we argued before. Perhaps we shouldn't worry about it. But then they pointed out, AMS pointed out that you can actually consider the following experiment. There's a time-like trajectory which captures, again, most of the Hawking radiation. This observer is able to identify the qubit, the scrambled qubit A, which is maximally entangled with B. And then he can continue and cross the horizon, and he will encounter both B and C, where he can explicitly verify whether they're entangled or not. And if they are entangled, as Hawking would predict, then he will find that all these three systems are maximally entangled in a way which is inconsistent with the monogamy of entanglement.
So in other words, they got around the Hayden Preskel because you didn't need a signal to have been sent.
Yeah, and also
the existing structure of the vacuum.
exactly. I think so. Yeah, I think because these modes, they start from trans-Planckian energies, I mean super high energies. So you're allowed to use those modes. I mean, because they're sort of vacuum modes, it seems like we're allowed to use them. And we don't have this constraint that we had before, that the energy of that mode had to be below the Planck scale.
Yeah. And they go in, I mean, there is some Hawking particle be created at the time they jump.
Yeah.
Yeah, that's right. That's right.
I was just trying to.
Yeah.
Yeah. So, okay, so yeah. So these guys have pointed out that you can actually do this experiment, and as a result, this idea of they argue that the idea of complementarity cannot save the paradox because there is a single observer who can observe the violation of monogamy. Okay. Now, now another argument that also suggests that it's difficult to have a smooth horizon is the fact that
And this, of course, you will emphasize, but the one thing which does remain, though, even after AMS, is if the inside mode is not part of an independent Hilbert space, right?
yes,
Then
that's right. That's right. So another intuitive argument, which is sort of against the existence of a smooth horizon, is that if in order for the horizon to be smooth, we need these two guys to be entangled. But not only that, we need them to be entangled in a very particular state. So what I mean is you can have two spins which are maximally entangled, but you have a phase here, right? And all of those states have equal amount of entanglement, but they're different states. And if you look at the effective field theory of the infalling observer, you need the quantum state to be a very particular entangled state, not any random entangled state. So we have, naively at least, we have a quantum system, and it has, let's say, two subsystems, B and C. And what we find is that in order for the horizon to be smooth, we need the entanglement between these two guys to be very specific, the details of the entanglement to be very specific on a typical state, which is, it seems to be in contradiction with what we expect in statistical mechanics, where if you take a big system and you factorize it, the details of the entanglement between the two systems are generally randomized.
This is because, if I may say, if you take the Minkowski vacuum, right, and you cut it in two parts and you ask about the entanglement, for any typical state at low enough energies, the structure of that entanglement will be.
Yeah, I think the answer to that question would be that the Minkowski vacuum is not a typical state. If you work with a real Hamiltonian and you try to write down a typical state with respect to that Hamiltonian, you will get something which has a firewall.
Okay, that's
Yeah.
another way to say it. Or I was saying that the the states we think about don't change the very high ultraviolet nature of the
Right. Yes, that's right. Okay, so this is not a very precise argument. It's some intuitive argument, and also, yeah.
Just to continue that, I mean, if you take a quantum field theory,
Yes.
I mean, typical state would, without putting some local energy requirement, would be very jagged. But that's not a puzzle.
A typical state, you mean?
I mean,
So that would be very far from a vacuum in particular.
well, yeah, if you allow what's happening here to be very different from what's happening
Then,
there,
if you calculate the expectation value of the stress tensor at that point, it will be very high.
very high.
Yeah, so to have a firewall.
That's right.
That's the argument.
That's right.
Yeah.
I mean, we don't feel puzzled about that, right?
No, but then, yeah, but we have a firewall in that case. We have a very large stress tensor.
No, we just say that for reasonable experiments, we're not in a typical state. We're in a state where
Yeah, okay, yeah.
a small.
That's right. So the question here is whether we want that a typical black hole state has a smooth horizon or not.
With some local constraints, maybe.
Well, so as we will discuss later, a possibility is that, well, okay. So the Bekenstein-Hawking
Yeah,
network.
I'm probably not understanding you. I'll just say it again. You know, you could probably in a quantum field theory make a state with not very high energy, but very high energy density at some point.
Yes.
It becomes very jagged. Those states are not created in typical experiments.
Yeah, that's what I was also saying. But that's because we start with the Minkowski vacuum and we create.
We do something reasonable.
So that's the sense in which everything we do creates, the typical states we create doesn't change the deep ultraviolet.
Yeah, because you have sort of decided that you will start with a state which is like a smooth respect to Minkowski Hamiltonian and perturb it a little bit. The equivalent statement would be to take the real Hamiltonian as your Hamiltonian, the Lorentz boost generator, and try to define a typical state with respect to that notion of energy. And that typical state would have very large stress tensor. Because the point is that in at least in AdS-CFT, the boundary Hamiltonian, which is what can be used to define a notion of a typical state, plays the role of a boost generator near the horizon.
I see. So you say this is a puzzle when seen from the point of view of the boundary.
It's more well phrased if we phrase for AdS.
The bulk I don't see much of. We start with a reasonable initial condition.
Yeah. Okay. Yeah. So regarding that, then we have to address one more question. So the Bekenstein-Hawking entropy gives you some.
I think he's agreeing with you. I mean, by saying it's because you have a rather particular state.
Yeah. So in particular, some people have argued that perhaps typical black hole microstates have firewalls, but the ones that you form by gravitational collapse, at least at early times, do not. Those are the special states that you're talking about. We start with some smooth initial data, we let the thing collapse, and then we want to ask if that particular state has a firewall or not, right? But that does not represent the typical state determined by this ensemble, right? Because I think there's some estimates, at least, I don't know how precise they are, but if you estimate the number of microstates you can form from gravitational collapse, it does not scale like m squared. So this entropy scales like m squared.
But could it be that so then the typical state is not smooth, but that's
Yeah.
relevant to physics?
That's a possibility. But it would imply that, for example, in AdS-CFT, when we consider a large black hole, if we take let's say a superposition of energy eigenstates, that would not be a smooth geometry. So most of the states counted by this formula would not have a smooth geometry. That's a logical possibility, yes.
But I didn't, and you'll probably come to this, that I didn't understand your comment that when viewed vis-a-vis the boundary Hamiltonian something or the other.
Yeah, so
it's not like the Ringler Hamiltonian, right?
sorry, I was just saying that if we define the notion of a typical state in the CFT, we will fix the energy, right?
Right.
So we would fix let's say the expectation value of the Hamiltonian. The Hamiltonian acts like that.
Yes,
Yeah.
you're right. So you're saying from the point of view of the boundary theory, it's an issue. Why? But even there, I mean, we expect to create reasonably smooth geometries by acting with boundary operators. No?
Well, I don't know. I think if you create this black hole by throwing some stuff from the boundary, then it could be that these black holes have a smooth horizon, but these are not the typical states that you would count if you were doing statistical mechanics in the n equals 4, and if you were fixing the total energy. This is a subset of those states.
Right.
So it's a logical possibility that this subset has a smooth horizon, while states that you form by just starting with, just a pure state.
Crazy experiment of
Yeah, yeah,
It's a
yeah,
very
yeah,
basic
yeah,
stuff.
yeah. Right.
Very crazy, but can I ask something?
Mhm.
Well, if I'm diverting you,
Mhm.
we can discuss later.
Mhm.
But if you create a typical state as seen in the boundary by
Mhm.
turning on some source,
You cannot do that, right? I mean, if you want to create a typical state, you have to take the source to be complicated, or you cannot do a quench and produce a. I mean, like by throwing some, if you perturb the n equals 4 by some single trace operator to throw in some matter, that will not be a pure state, a typical state. If you keep perturbing the state over a very long time with many operators, or if you produce the state by something very complicated, then it may be typical.
You can estimate that by computing the entropy of the gas,
Yeah, right.
which scales like e to the power 9 by 10.
Right.
Which at e is equal to n squared is smaller than is n squared n to the power 18 by 10, which is smaller than n squared.
for the single trace guys.
Yeah, because single trace create a gas in the bulk, a graviton gas.
Yeah, that's smaller than the black hole.
Yeah.
I see. So typical single trace operators will create fewer states. Okay.
Yes. So
But, I mean,
yeah.
but at least these states will correspond to smooth geometries.
Yeah, and maybe that's all that's needed for
Yes. Yes. Yes.
physics.
Yes.
And, I mean, what I'm
Sorry.
saying is that Hawking said that, look, I'm going to assume that the horizon is a smooth place. It's either what we would now say is either the Unruh vacuum or whatever, and then I'm going to say you get Hawking radiation, right?
Mm-hmm.
And so if you're going to study the paradox his work raises, we have to take a situation where you get a reasonably smooth horizon, and then ask what's happening in there.
And it comes out of his calculation. You just solve the equations of motion, you do get a smooth horizon.
Right, right. I mean, all I'm saying is that, okay, suppose we had a very atypical collapse where you didn't get anything like a smooth horizon. You might happen, but then, okay, that's not what Hawking was talking about.
But I mean, you would expect that.
As long as there's reasonably enough situation.
Okay, but I would say also you would expect that perhaps if you produce a state by something very crazy, something complicated, and if you wait long enough, naively you would expect that the black hole will stabilize again into something which has a smooth horizon at late times. But what we're saying here is that, well, so the question is, okay, even if you produce a state by something complicated, do you expect that at late times it will have a smooth horizon? So if you argue that typical states do not have a smooth horizon, then this means that no matter how long you wait, there will always be something there, right?
I see. Okay, that's an interesting question. I see. But I'm saying just to address Hawking's original question,
Mhm.
this paradox, you could say, okay, I'll just create the states which give rise to a smooth horizon. I think we can create them, for example, by turning on single trace operators
Yes.
for some time, and then ask about the information problem.
Okay, but there are some other refinements I think which we can perhaps discuss tomorrow, where I think, yeah. So
Sure,
yeah.
sure. Okay, good.
So I can also define, yeah. So and I think a nice example is the following: if you take the eternal black hole, the two-sided eternal black hole, it has a smooth horizon, right? And you can also consider the family of time-shifted states, where you move only one of the two boundaries in time. So by doing that, you generate a very large number of states, where naively you would expect from the arguments in gravity that all of those should have a smooth horizon, because they're related by a large diffeomorphism to the eternal black hole. So you have a family of geometries which are related by large diffeomorphism. So it's an ensemble of states. It's not a typical state. It's much smaller than the typical state. But even within that subset, you can formulate paradoxes, as I will perhaps explain in today's. Yeah. Okay.
So, and
Yeah.
to ask, does everyone agree that the eternal black hole in a standard state has smooth geometry?
Maybe I don't know if Samir agrees. He has written some papers where he questions that, but I think most people
And
agree.
would agree, for instance.
Well,
There's a disagreement on
I asked.
I'm just wondering.
Well, yeah.
Just to understand the question, if you take the double-sided situation in AdS, you take what we would call as a thermophile double in the boundary theory, there's still some disagreement whether it's a smooth eternal.
I'm not sure. I think most people would agree that specifically the thermophile state. So if you write exactly the state, well, I'm sorry. Let me think for a second.
Yeah, just exactly.
So you take exactly the state.
Yeah.
Now, Samir Mathur and maybe Borun Choudhury and some other people have written some papers where they point out some problems with this state having a smooth horizon. I think Marolov and Wall have also written a paper where they sort of identify some kind of conceptual paradoxes if we assume that this has dual. I can talk about it tomorrow if you want, maybe. But what I was saying before is that, but apart from that, I think most people would agree that this has a smooth horizon. And the argument I was making is that if you take this state and if you evolve it like that, so you evolve only one of the two sides with Hamiltonian. In the bulk, that is a large diffeomorphism, where you have the same geometry, but you glue it on the boundary at different times. It's sort of trivial, right? You take the same geometry, but you glue it differently to the boundary. So you would, if this has a smooth horizon, then this should also have a smooth horizon, right? And then you can take this T to be very large, and in this way you can generate a very large number of ensemble of states, and then within that ensemble of states you can derive a paradox. That's something we did with Subrat, and the only way that we propose that it's resolved if the operators depend on the state, but if you don't want to do that, then there's a paradox.
Do you propose that it's resolved if what?
If you allow the operators in the interior to depend on the microstate, then it's resolved. But if you don't want to do that, if you insist that they are the same operators, then this set of states cannot all of them have a smooth horizon. Roughly, the idea is that by superimposing many of those states, you can remove the entanglement between the two sides, and then. Yeah. Okay. Yeah. So then, all right. Let's see then.
We have 2 lectures on Thursdays.
Yeah. So okay, maybe that's a good point to stop. I mean, we have identified.
Doing great. You leave on Thursday night, is it?
Yes, that's right.
We have an absolute cutoff.
On Wednesday and Friday are holidays.
I'm really sorry, otherwise you folks would have wanted to have one today.
No, it's great to have you around.
Okay, so here we have identified some problems for black holes in flat space. Some of these paradoxes were not very precise. I mean, we had to worry about defining the entanglement in a region in gravity. There were many questions, but I think if we now go to AdS CFT, we will be able to make this paradox a little bit more precise. So we'll try to consider large black holes in AdS and try to formulate a set of paradoxes which seem to suggest that they don't have a smooth interior.